Hi, welcome to Chapter 10, Part 3. In this part of the lecture, we will be looking at the work-energy theorems. So the two work-energy theorems we're going to look at are, the first one is called the work-kinetic-energy theorem, and the second is the work-energy theorem for contact forces. So let's begin. The work-kinetic-energy theorem states that the change in kinetic energy of a system is equal to the total or net work done on the system by all forces present. So we can write the work-kinetic energy theorem as follows. The net work is equal to delta K, where K is the kinetic energy. So W, or work sub net, is the net work done by any and all forces present. Another way to think of this is the net work here is the work that's done by the net force, which includes, again, all the forces present. So this might include friction, gravity, air resistance, spring forces, and all so-called contact forces, which we'll talk about later as well. But contact forces include pushing, pulling, lifting, tension, normal force, thrust. So any force that's present will have to be included in this theorem here. So let's go ahead and just start working through some examples to make sense of this. So in this first one, we've got Joe's 1,000 kilogram car has run out of gas. He gets out and starts pushing it with 500 newtons of force. How fast is the car moving after he pushes it 10 meters? And we will neglect friction in this problem. So this is one of those problems that could be solved in several different ways. We could go back and solve this certainly using Newton's second law, determining the acceleration of the car, and then working with kinematics equations and so forth to find the final speed of the car. What we're going to do here is a little different. It's a more direct approach of solving problems, and that is whenever we can use energy or work, it often saves us some steps. So we're going to use the work-kinetic-energy theorem and say that the net work that is done in the car is equal to the change in kinetic energy of the car. So what is the net work? Well, it's the net work that's done by Joe. The only force that does work on the car is Joe's push. Gravity and the normal force do no work because the car doesn't move in the vertical direction. So since this car is just moving horizontally in this problem, the gravitational force down and normal force up do not do any work, so we can just ignore them. All we have to do is include Joe's push. So the work done here, the net work, is just the force of Joe pushing times the distance. On the right side, we have the change in kinetic energy, which is the final kinetic energy minus the initial kinetic energy. And since the car is initially at rest, this term here is 0. So on the right side, we just have the final kinetic energy, which is 1/2 mv squared. Remember, that's our equation to determine kinetic energy. So here is our this is basically our statement of the problem. This is the work done over here, and this is the change in kinetic energy here. And one thing we notice here is that this V here is the answer we're looking for. We want to solve this for velocity. So this is why this method is more direct than using Newton's second law to find acceleration. And then from acceleration, we can use kinematics equations to find final velocity. Here is our answer right here, basically, in one of the first steps of this problem. So all we have to do is solve for V. So we can get rid of the 1/2, multiply by 2. We can divide by the m. So we get V squared equals 2FD over m. And then to solve for V, we just take the square root. So our velocity is equal to the square root of 2 times the force times the distance divided by the mass. So here we can plug in those values. The force was 500 newtons, the distance was 10 meters, and the mass of the car was given as 1,000 kilograms. So you have to evaluate this in your calculator, take the square root, and the answer is 3.2 meters per second. That's how fast this car is going after he pushes it 10 meters. One thing, just kind of stepping back and looking at the big picture here, basically what's happening here is Joe is doing work. And remember, when we do work, we transfer energy to an object. So what this car has gained is kinetic energy. And where did that come from? Well, it came from the work that Joe did. Here's a little bit different problem. This is, in this example, we're going to use the work done by gravity. So let's say you jump off a 15-meter tall cliff into the water below. What's your speed when you hit the water? So again, this is a problem that could be solved in several different ways. We learned how to solve these types of problems when we studied kinematics and projectile motion in the first few chapters of the course. Let's take a look at this from a work and energy perspective. Also, we're going to ignore air resistance here. The only force that does work on your body is gravity. So if you think of the free body diagram here of the person jumping, there's just a weight force down and that's it. So the only force that's doing work is gravity. So we're going to calculate the work done by gravity, and that should be equal to the change in kinetic energy of the person. So the work done by gravity, as always, is force times distance. Now, what is the force of gravity? Well, it's weight, which is mg. And what is the distance that the gravity is working over? Well, it's the height that you're falling, right? And that's 15 meters. So that's the change d to h. And on the right side, again, we have the change in kinetic energy, delta K. So it's K final minus K initial. K initial is again 0. When we start at the top, we're at rest. So the initial kinetic energy is 0. So the final kinetic energy is 1/2 mv squared. Now we can simplify. Both sides have an m for mass. We can cancel that out. And finally, we can solve for v squared first. Let's multiply both sides by 2. Get rid of the 1/2, take the square root, and we get v is equal to square root of 2gh, where g is 9.8, and the height h is 15 meters. So these numbers, multiply them together, take the square root of the whole thing, and we get 17.1 meters per second. So in this case, what's happening is gravity is doing work on you when you jump. And remember, whenever we do work on something, we change the energy. We add energy to that object. So we're gaining kinetic energy in this case. Let's look at another example here. This is to calculate the stopping distance of a car. So let's say you're driving at 25 meters per second and have to slam on your brakes to avoid hitting a pedestrian. How far do you skid before stopping? Assume the car's mass is 1,500 kilograms and the coefficient of kinetic friction is 0.8. All right, so the only force that does work on the car is friction. Remember, gravity going down and normal force going up, well, those are in the vertical direction. The car is moving horizontally on a level road, we're assuming here. So also, friction does negative work because the force acts in the opposite direction as the motion. All right, so this is a case where the force is going against the motion, which is technically negative work. So let's see, I mentioned the gravity and normal force do no work. Okay, so let's go ahead and solve this problem. So let's calculate the force of friction first. The kinetic friction, F sub k, is equal to the coefficient of friction mu times the normal force. And the normal force is the weight of the car, which is mg. So mu is 0.8. The mass of the car is 1,500 kilograms, and g is 9.8. And this gives us 11,760 newtons. Remember the minus sign in there because the friction force is pointing against us. So we're going to put that minus sign in there. The initial kinetic energy of the car, let's calculate that next. Initial kinetic energy is 1/2 mv squared, where again the mass is 1,500 kilograms, and v is the initial velocity of the car, 25 meters per second. So this comes out to be 469,000 joules. All right, this is a large number of joules, obviously, because we're talking about a big, heavy object that's going very fast. That's why there's so much kinetic energy. So the Work-Kinetic-Energy Theorem says that the net work done is equal to delta K, the change in kinetic energy. So the net work done is the work done by friction. Remember, that's the only force that's doing work. And that's equal to delta K, which is K final minus K initial. The final kinetic energy of the car, remember, is 0 because it has stopped. The initial kinetic energy of the car is this number here, 469,000. So our change in kinetic energy is minus 469,000 joules. And again, the minus sign just means the kinetic energy, it went down. It reduced because the car slowed down. Okay, so we've got the work done by friction is equal to force times distance. And the force is, of course, the friction force, F sub k. So the friction force times distance is negative 469,000 joules. So let's solve for d, the distance of how far the car skidded. That means how far did friction do, what was the distance that friction actually did work on the car. So this number up here, negative 469,000, that's the number of joules. And then we have to divide by the friction force, which remember we found in the first step. It's negative 11,760. And so these minus signs cancel, but if you do the math here on your calculator, you'll come up with a distance of 40 meters. Let's now take a look at an example with a spring. So a toy dart gun shoots a 10-gram dart at 15 meters per second. So here's kind of the before picture, and here's the after picture with the dart shooting out of the gun. The spring was compressed 5 centimeters to load the gun. Find the average force of the spring. So again, we can use the Work-Kinetic-Energy Theorem here. The work done by the spring is the net work here. The only force that's acting on this dart is the spring pushing on it. Gravity is acting downward and is not doing any work to shoot the dart out horizontally. Okay, we're assuming in this picture that the gun is shot horizontally. Okay, so since the gravity is in a vertical direction, it doesn't do any work. So our net work is the average force of the spring times the distance that the spring pushes on. And that is equal to the change in kinetic energy. Now the change in kinetic energy of the dart is just equal to 1/2 mv squared. This is the final kinetic energy of the dart. Remember, it starts at rest, and its final kinetic energy is 1/2 mv squared. So we're trying to solve for this average force here. So all we have to do is divide both sides by d. So the average force is mv squared over 2d, and we can plug in all our numbers. For the mass of the dart, remember it was 10 grams, so that's 0.01 kilograms. The velocity is 15 meters per second. We have to square that. And down at the bottom, we were told that d is how much, that's the distance that the spring is pushing on the dart. That's 5 centimeters, which is 0.05 meters. So this all comes out to be 22.5 newtons. So here's another example similar to the one before. Remember Joe and his car that ran out of gas. So this time, suppose Joe has to push his 1,000 kilogram car up his sloped driveway into his garage. So you can see the situation here. He's pushing it up this driveway. The driveway has a length of 20 meters and it's 2 meters tall. And he's going to push it up into the garage up here. So he's pushing with 1,000 newtons of force, we're told, the whole way up the driveway. The question is, how fast is the car going when it gets into his garage? And again, we're going to ignore friction. So this is another good application of the Work-Kinetic-Energy Theorem. The net amount of work done is equal to the change in kinetic energy. Now, what makes this problem a little more tricky is that both Joe and gravity are doing work on this problem. Joe does positive work because the car moves in the same direction as his push. He's pushing it up the hill here. Gravity, however, does negative work because the gravity force pulls down, but the car moves up. So since the car is moving up 2 meters, but gravity is pointing down, gravity is actually doing negative work here. So over here on the left side, the net amount of work is the work done by Joe minus the work done by gravity. So we're going to subtract mgh here instead of adding it. And then the work done by Joe is Joe's force, F sub Joe, times the distance. And on the right side, we're trying, this is the change in kinetic energy. So the final kinetic energy is 1/2 mv squared again. The initial kinetic energy is 0 because the car is assuming we're starting at rest at the bottom of the driveway. So at this point now, we've just got it's just a math problem. We need to solve for the speed v of the car. So to do that, I've rewritten the equation here with velocity 1/2 mv squared all on the left side. And then we have f Joe times d minus mgh on the right side. Multiply everything by 2 to get rid of the 1/2. So here's the 2 over here. Divide by m to get rid of the m, so there it is, and then that leaves us with v squared, and then finally we take the square root. So here is our answer in terms of just the variable names there, and now we can plug in all of the numbers. We've got the force here, F is 1,000 newtons, the distance d is 20 meters, that was the distance up the driveway. M of the car, mass of the car is 1,000 kilograms. G is 9.8. The height, H here, is the 2 meters that the car actually rises up above the ground. And then on the bottom, again, is the mass of the car, 1,000. So this all comes out to be 0.89 meters per second. Just a note here. So what's happened? This problem is a little different because we have two different forces that are doing work. One was doing positive work and the other negative. And so, one of the tricky things of this problem is to remember that the gravitational work done, MGH, we have to make sure that is counted as negative because that works against the car. So in the second part of this part of the video, we're going to look at another work-energy theorem, and this one is specifically for contact forces. So the work-energy theorem for contact forces, the first thing we need to do is clarify and define what is a contact force. A contact force, remember, when we first started talking about forces, it's whenever there is direct contact between the agent of the force and the object that is being acted on. So for example, whenever you push on something or pull on something, whenever you lift something, whenever there's tension in a rope or a spring, or not a spring, whenever there was tension from a rope or a cable or a string, thrust is a contact force because we're basically we're pushing on the object directly. And the normal force is considered a contact force because, of course, normal force is when an object is in contact with the surface. Now, things that do not count as contact forces, friction. All right, now you might say, well, wait a minute, friction is when things rub against each other. Well, friction is a different type of force, which in more advanced courses we call a dissipative force. In other words, friction sort of steals energy and turns it into thermal energy. It's a different type of force. Gravity or weight, that is not a contact force. The spring force is not a contact force. In fact, gravity and the spring force are called conservative forces, and those are different than contact forces. And also drag is like friction. It's a force that dissipates energy, so it's not a contact force. So now that we've sort of clarified between the two types of forces, when a contact force does work on an object or system, it increases the energy of the object or system. So let's just do a couple some thought experiments here, just some conceptual examples. Imagine that you push a box across a table. You slide it across the table by pushing on it. So the work done by your push is equal to the increase in kinetic energy and thermal energy, all right, of the box. When you lift a ball, the work that you do increases the potential energy of the ball. When you compress a spring, the work that you do by pushing on the spring increases the spring's elastic potential energy. When you stretch a rubber band, again, you're pulling on the rubber band. So this is a contact force. The work that you do increases the elastic potential energy of the rubber band. If you throw a ball up in the air, well, how do you throw something? You push on it, right, with your hand. And so that work done leads to an increase in the ball's kinetic and potential energy. So to kind of summarize all of this and formalize it, we come up with what's called the work-energy theorem. The work done by a contact force on an object is equal to the total energy given to the object. So we can write this as an equation as follows. The work done by a contact force, work sub contact, is equal to the change in the total energy of the object. Now, what do we mean by the total change in energy of the object? Well, we mean the sum of the change in kinetic energy, the change in the potential energy, and the change in the thermal energy. Now, not all of these may change, but they all might change. So we include them all here in the formula, and when we work on the specific problems, we won't have to always include all these terms, but we have to consider them. So let's go ahead and look at some examples. So let's start with a pretty basic one, the act of lifting weights. So a woman lifts a 25 kilogram barbell from the floor over her head to a final height of 2.2 meters, as you can see in the picture there. The bar is at rest above her head, so she's just holding it there now. What is the average force that she exerted during the lift? So the only contact force on the barbell is the woman's push. Gravity, remember, is not a contact force. So we don't include gravity. We just include the fact that she's pushing up on this bar. So according to the work-energy theorem for contact forces, the work done by a contact force is equal to, remember, delta K plus delta U plus delta E thermal. Well, there's no change in kinetic energy because she started with the bar on the floor at rest, and at the end, the bar is at rest above her head. So it's still not moving, right? You know, it did move while she was lifting it, of course, but we're talking about here at the end after it stopped. So delta K is 0. What about thermal energy? Well, again, this bar is not rubbing against anything, so there's no friction, all right? You can argue that, well, there's friction inside of her muscles. We'll deal with that in the next chapter. But regarding the bar, the bar did not experience any friction. So delta, the change in thermal energy is also 0. So all we have is the change in potential energy. Obviously, this bar started on the floor and it ended up over her head. So the bar has gained gravitational potential energy. So the work done by her push is her force times the distance. And the change in potential energy is equal to the final potential energy minus the initial potential energy, which is 0. Because remember, the bar started on the floor. It didn't have any gravitational potential energy. So what is the distance that she lifts the bar? Well, it's the height that she lifted it, right? Which was 2.2 meters. We'll put in our numbers later. Over on the right side, we have, remember, gravitational potential energy is given by mgh. So notice the h here cancels the h here, and we're left with the force is just equal to the weight of the bar, mg. The bar has a mass of 25, and g is 9.8, which gives us 245 newtons. So this problem, obviously, this is a case where we sort of overthought the problem. We might have been able to guess this answer just by thinking about it. If you want to lift something, remember you need to apply the amount of force equal to the weight of the object. And that's just what this says right here. Her force was equal to mg, the weight of this barbell. So, we could have, in a sense, just answered the problem there. The reason I show this problem with all these steps here is to give you a sense of how to use the work-energy theorem, in this case when gravity, I'm sorry, not gravity, but when we're lifting something up. Let's go ahead and do another example. So this is the same problem that we just saw a couple slides ago with Joe pushing his car up the driveway. Now the difference here is we're going to solve it a different way. We're going to solve it using the work-energy theorem for contact forces, which is different than the work-kinetic-energy theorem, which included all forces. So everything else is exactly the same. Remember, Joe's pushing his car up a 20-meter long driveway. The height of the driveway is 2 meters. The car has a mass of 1,000 kilograms, and we're trying to figure out how fast the car goes when he gets up into the garage here. And we also know that he pushes with 1,000 newtons of force. So let's redo this problem now with the work-energy theorem for contact forces. So we start by writing the work done by a contact force is equal to delta K plus delta U plus delta E thermal. We're going to ignore friction here, so this last term is 0. There is no change in thermal energy. So the work done by the contact force is equal to the final kinetic energy, that's the delta K, plus the final potential energy, that's the delta U, because both of these, kinetic and potential energy, both start at 0 down here. The car is at rest and it's at 0 elevation. Now, what about, remember over here we have to include all contact forces. The only contact force on the car is Joe's push. Gravity is not a contact force. So both kinetic and potential energy increase. Ignoring friction, there's no change in thermal energy, which we already talked about here. Okay, so the work done by Joe's contact force is his force times distance, and that's equal to the final kinetic energy is 1/2 mv squared. The final potential energy is mgh. And again, we're going to solve for v. So I put the v with the 1/2 mv squared over here on the left side, and we get force times distance minus mgh. We've solved for v by multiplying by 2, dividing by the mass, and this looks just like what we had before. And in fact, it is. We end up with the square root of all this stuff inside. I won't read it all out, but it's, we have all these values of force, distance, mass, g, and the height. We put that all in there, and we get the same answer as we did before, 0.89 meters per second. This just shows that, there is more than one way to approach these problems. This one, we didn't have to use the gravitational force doing work. We had to do that in the last problem because we had the total work over here on the left. But when you were dealing with contact forces, we only have to include the contact forces that do work here. And on the right side, before we only had the change in kinetic energy, now we've got the change in all types of energy. Let's look at another example. This is similar to the dart gun problem that we saw before, with just this is approaching it a little different way. A spring-loaded toy dart gun has a spring constant of 500 newtons per meter. Here's the spring all coiled up. To load the gun, the dart is pushed into the spring 5 centimeters. All right, so we push this dart in here, it compresses the spring, and a little latch holds it there, and then when you pull the trigger, it releases the spring, which pushes the dart out of the gun. So question A, how much elastic potential energy is stored in the spring? So let's answer that first. So part A, remember that elastic potential energy, we saw this in an earlier part of this chapter's lecture. The spring potential energy is given by 1/2 K delta X squared. All right, this is our equation for elastic potential energy. So I have 1/2 times the spring constant, which is 500, and delta X, that's how far the spring is pushed. So it's 5 centimeters, which is 0.05 meters. And remember, again, we have to square that value. So when you do all this math here, you end up with 0.625 joules. Question B, how much work do you do when loading the gun? Well, remember the work-energy theorem says that the work you do by pushing the dart in, right? This is the work done by the contact force of pushing, is just equal to the change in the energy of the spring. So that's the only, there's no change in kinetic energy because it's not moving when we're done here, when we push it in. And then there's no friction, so there's no change in thermal energy. So what this basically says here is that the work that you do to push in the dart is equal to the amount of energy that's stored in the spring. And we know what that is. It's 0.625 joules, so that is our answer. The last part here, what is the average force needed to push the dart in to load the gun? So we know that work done is equal to the average force times the distance. So the average force is equal to the work divided by the distance. The work, remember we figured that out right here, is 0.625 joules, and we divide it by the 5 centimeters, convert it to meters, of course, so 0.05 meters gives us 12.5 newtons. Here's our last example and slide from this part of the lecture. Let's take a look at a problem that talks about rocket thrust. So a 1,000 kilogram rocket blasts off from rest on its launch pad. The rocket's engine provides 20,000 newtons of thrust. How fast is the rocket going when it reaches a height of 300 meters? Ignore air resistance. So this is another one of those problems that we could solve using several different methods. In this case, we're going to use the Work-Energy Theorem for contact forces. All right, so remember what it says is that the work done by contact forces is equal to delta K plus delta U plus delta E thermal. Now, since we're not including air resistance, there's no drag or friction present, so delta E thermal is 0, so we can ignore that. The work done by the contact force, so we have to figure out, all right, what are the contact forces acting on the rocket? So here's the rocket, and its free body diagram would have two forces. It would have weight down and thrust up. But remember, weight is not a contact force. We do not include gravity as a contact force. So the only contact force present is the thrust. So over on the left side, we have this is the force times distance here. We'll replace that F with a T for thrust. And the distance that it travels is the height that the rocket goes, H, while its engines are burning. On the right side, we have the change in kinetic energy, which is K final minus K initial. But since the rocket starts at rest on the Earth, its K initial is 0. And then delta U, that's the change in gravitational potential energy, U final minus U initial. And again, since the rocket starts on the ground, it has no initial potential energy. So all we have on the right side is the final kinetic energy, which is 1/2 mv squared, and the final gravitational potential energy, which is mgh. So this is our equation right here, and we are trying to solve for the speed, right? The velocity of the rocket, how fast is it going? So we're going to solve for v, which is right here. So we can already see our answer, in the equation. It's just a matter of doing some algebra now to solve for v. And this is nothing different than we've done in some of the other problems. We have to move this term all by itself. So we have 1/2 mv squared equals th minus mgh. Multiply everything by 2 to get rid of the 1/2. Divide everything by m. And we get v squared is all this on the right. And then to get v, we just take the square root of all this, and we get this expression right here. Now we can fill in our numbers. T, remember, was the thrust of the rocket, so that's 20,000. H is the height that the rocket goes up. Well, that was given to us too as 300 meters. The mass of the rocket was given as 1,000 kilograms. G is 9.8. And here's the height again, same H as here, so that's 300 again. And then the mass shows up on the bottom in the denominator, which is 1,000 kilograms. So carefully doing all this, remember there's some parentheses here. Do this in your calculator, take the square root when you're done, and you'll come up with a final speed of 78 meters per second. So that was part 3 of chapter 10 on energy and work and energy. So we'll reconvene in part 4 when we'll talk about the conservation of energy principle. See you then.